Okay, so before we start, I want to do some self-promotion. So I'm organizing a conference with some other people in Hangzhou this year, November 2 to 6, called Arithmetic Algebraic Geometry in Hangzhou. If you Google the title, you'll find the website. So yeah, everyone is very welcome. So the focus is a little bit different. It's not quite 100% Langlands, but yeah, it should be fun. Okay, so I want to talk about charts and compact generation. So this is sort of almost completely orthogonal to what I talked about yesterday, but nevertheless, it's, I think, an essential part of the Fark-Schulze geometry. So charts are, let me sort of say, essential geometry. And they also show up, well, how should I say it? If you, I guess Ian will talk about this next week, but there's this Bun G meromorphic to Bun G, and somehow magically out of this, the charts also appear. So, okay, I'm going to use charts to prove the category of Sheaves and Bun G is compactly generated, but that's just one application, and the charts are really, yeah, just an important part of the geometry in general. Okay, so yeah, let me pull up my notes. So I'm going to define, so we will define a kind of M with a map pi to Bun G. And I'll call it the kind of like, it'll be a sort of moduli space of filtrations. Okay, so on the right-hand side, I have like G bundles. So you could think of this, suppose that G is GLN, I have rank and vector bundles. And then on a vector bundle, of course, I can kind of consider a relative Grassmannian or something, right? So I can consider their moduli space of filtrations on this vector bundle. And okay, so that's more or less what we're going to do. And it will turn out that I mean, there's something interesting going on. Like if I give you a vector bundle, you can ask, okay, maybe my vector bundle can be written as an extension of two other vector bundles, and given these two other vector bundles, like which vector bundles can be written as an extension of them? So there's some kind of interplay between, like, how can I move through Bun G by taking like extensions and filtrations? So that's what we're going to study here. So for G is DLN. This kind of was explored in work of Hansen, and also, well, what should I say, Birkbeck et al. Like there's a, yeah, and this kind of Arizona Winter School group. So the wonderful Perfectoid Woodstock Arizona Winter School, 2017, I believe. I was there. Never forget. Anyway, one of the groups there wrote this really nice paper about extensions of vector bundles on the Fark-Fontaine curve. Okay, so let's try to make this precise. So G bundles on the relative Fark-Fontaine curve. Well, what are those? They're just the same thing as exact tensor functors. From rep G to this exact tensor category of vector bundles on XS. Okay, so this, I mean, this is explained somewhere in the Berkeley notes, the appendix to some lecture 18 or 19, I think. Okay, so I want to say what is a filtered vector bundle? Well, it's going to be a kind of exact tensor functor to some category of filtered. Sorry, what is a filtered G bundle is like exact tensor functor to a category of filtered vector bundles. So now I should define this category of filtered vector bundles. So I don't think, so in Varkschulze there is no notation for this, so I'm going to invent it. So let me call filtered Q vector bundles XS. Okay, so what is this? Well, it's a category of pairs E fill bullet E, where E is just a vector bundle. And this filtration, so fill bullet E is a collection of subbundles. E less or equal to lambda inside of E, indexed by Q, such that some properties hold. Okay, so there are the usual things. So if lambda prime is less than lambda, then E less or equal to lambda prime is inside E less or equal to lambda. So the filtration is increasing, and the union of all the lambdas of E less equal to lambda is E. That means the filtration is exhaustive, and the intersection over all lambda of E less equal to lambda is 0. Okay, so these increasing, exhaustive, and separated. Okay, and okay, you can turn this into an exact tensor category. So this can be turned into an exact tensor category. So the tensor products, okay, there's some formula for it that I'm not going to write down.
You kind of convolve the filtration system.
Yeah. And so it won't, this kind of thing is typically not an abelian category of filtered object, but it's an exact category.
There's no condition on the gradient pieces, is that correct?
No, not yet. Okay, so this is, so far I don't have any condition. Okay, I invented this definition just for now, so, I mean, yeah, in the literature people have some different things, but, so then so a Q filtered vector bundle on XS, or Q filtered G bundle, is just a tensor functor, is an exact tensor functor from web G to this fill Q vector bundles XS. Okay. So this, okay, this now I get some kind of modelized space. So this has a modelized stack of these. So that's not quite M, it's what I'll call M big. Okay. So this also is not a notation that's in Varkschulze. So okay, this is just something. I have Q filtered, yeah, just modelized space of Q filtered. Modelized stack of Q filtered G bundles on the Vark-Fontaine curve. And of course, there's a forgetful functor to I guess there's a G, right, M to Bun G, where I'm just forgetting the filtration. Okay, because, yeah, so maybe I didn't write this down, but, okay, fill Q vector bundles S has a forgetful functor. Okay? And M is just, M is a kind of subfunctor of M big, where I put some condition on the associated graded. So there's forgetful. This function we've already seen, fill Q. I don't know. It sounds a bit scary to me. Yeah. I guess I just invented M big last week, so yeah. If you want to prove that, that'd be nice. Okay. Yeah, it's somehow like.
I think M big is going to be like reasonable.
Yes, right? Because it's like, okay, so what are you doing? You have like the disjoint union of all the flag varieties, relative flag varieties over your Fark von Tennen curve, and you're just taking sections of that. So that sounds like it's supposed.
The lambdas are like discrete data because they're like human.
Yes, yeah.
It's huge, but it's still like not evil.
Right. So it's. I think it's. It should be okay. Okay. So this is forgetful from. And also an associated graded. Functor. And what this does, it sends, so I'll call this Q, and Q of E fill bullet E is the direct sum over all lambda of E less or equal to lambda, E strictly less than lambda, where E strictly less than lambda is the union lambda prime less or equal to strictly less than lambda of E less or equal to lambda prime. Okay, so basically like at all points, finally many points where the filtration jumps, I look at what the quotient is, and that's my associated graded. So yeah, if you look at this, so vector bundles on the Fark von Tennen curve, there's already somehow a Q index thing, which is the slope, right? So M inside M big is the, I guess there's a G here. So is the sub-functor, substack. Where, so I look at functors, it's a substack of tensor functors. Exact tensor functors E. Such that for all kind of representations, if I look at rho push forward of E, so if I look at this associated graded, so this is semi-stable of slope lambda for all lambda. Okay, so this is just a natural condition to put is, I have like now, I just want, it is a natural condition to put. Okay, and this is sort of, okay, so of course most of these, for most lambda, this will be 0, and okay, I guess the 0 vector bundle is semi-stable of any slope. So this makes sense. Okay, so this is just a definition of M, and so M comes with two functors. So the first is just the forgetful one. So forgetting the filtration, and the other one is Q, which is like associated graded. And this goes to what? Well, it goes to the modelized space of like semi-stable vector bundles of, and that in G bundle language is the direct sum of B and BG of point mod GBQP. Okay? And then, so this tells us that M is a disjoint union over B of MB. And I also have a kind of pi B and a QB. And I have a kind of Cartesian diagram MB tilde over MB mapping to point mod GBQP. And this just maps to the point. So there's a natural torser over here. Okay, so yeah, it's basically saying, yeah, if you fix the lambdas, then there's an open and closed substack. Zoom out. Oh, that's a good point. Yeah, let me.
Just to make sure I understand, you could have defined like fill big instead of calling it like fill or whatever, right? And then this would be like, this condition on the gradients would cut out some like sub condition that's stable under convolution.
Right, I guess I could have defined a
I'm not asking you to change anything.
sub-exact tensor category, yeah.
So you're asking that the filtrations go the wrong way somehow compared to the corresponding filtration.
Yeah. Okay, and there's one more thing which is important, which is that this map Q has a section. Okay. Yeah, I get that Q from the earlier Q.
Can you explain that a little bit?
Okay, so when G is GLN, if I give you a filtered vector bundle, all of whose associated gradients are semi-stable of a certain slope, then the associated gradient gives me a semi-stable vector bundle with a certain slope kind of co-character, and that and the locus where that's true is open and closed. Certainly it's open because being semi-stable, this is open, but it's also going to be closed because it's sort of like, it puts you in a component of Bun G. And then I'm saying, okay, so this gives me a disjoint union over all possible like tuples of slopes which give you a vector bundle of rank n. And the automorphism of a semi-stable vector bundle of that slope that fix the slope filtration, or sort of fix the slope decomposition is precisely this point mod GBQP. Yeah, thanks for the question. Okay, and okay, so this map Q has a section. Okay, so the notation in Fark-Schulze for this section is kind of bad, unfortunately. They call it, so they call it I. And of course, I don't want to write IB because IB means something else already, although it's related. But okay, if I give you a semi-stable vector bundle, like a direct sum of semi-stable vector bundles, I can put a filtration on that. Okay, I just put the kind of obvious split filtration, or maybe the opposite one. So that gives me a section of this. And if so that gives me a map from point mod GBQP to M. And then you can ask so yeah, like what is this map here? So there's a map here induced by the section, and you can ask what that map is, and it's the obvious one, which just takes a semi-stable vector bundle and considers this as a semi-stable G bundle, considers it as a G bundle. Okay, I think this took me a while to figure out. This is sort of implicit in the discussion in Fark-Schulze, but it is kind of useful. So let me just write. This is the obvious map. So it's not quite I upper B, but it's, yeah. Okay, are you with me so far?
Will you do an example?
Yeah, I will do an example. Yes. That's the next thing. Okay, so let's immediately do, so this example is the next thing. Okay, so G is GLN, and so I fix a B, and I'm going to write it as, so it's a direct sum of two semi-stable vector bundles, where E1, E2 are semi-stable of slopes lambda 1 strictly less than lambda 2. Okay. So then, so I could ask, like, what is MB? And so I'm going to tell you what is MB tilde, okay? So MB would be like extensions of E1 by E2, or like is like filtrations where the graded pieces are abstractly isomorphic to E1 and E2, whereas MB tilde is just extensions of E1 by E2. So MB, okay, so I always get confused with the direction, so let me just write, this should be is the moduli space of extensions. And I hope I'm getting the 1 and 2 right here. Okay, so it's a moduli space of extensions. Okay, that doesn't sound so bad, right? And so this is something that also comes by a different name, which is so it's a moduli space of extensions over FP bar, right? So E1 and E2 are defined over FP bar, and so MB tilde is this moduli space of these extensions, and this also has another name. So one fruitful way to think about this is equivalently. It represents this functor sending, so the functor sending a perfectoid space S to H1 on the Vark-Fontaine curve of S of E2 dual tensor E1. Okay, and so what are we doing here? We're taking a vector bundle, E2 tensor E1, well, the slope of that is strictly negative by my assumption. And so taking H1 of a strictly negative slope vector bundle, that's a nice thing. That's called a negative Banach-Gomez space. So it is. So it is a negative. Maybe it's an absolute Banach-Gomez space, right? Because it lives over negative absolute Banach-Gomez space. Okay, so those are very nice geometric objects. Okay. In particular, that means that the map it's going to be homologically smooth. Okay, so maybe let me just sneak in some notation here. This map is QB, and I'll call this Q tilde B. So this implies that QB and Q tilde B they're representable in locally spatial diamonds. Okay, so this is one of these conditions. If you open a Talk homology of diamonds, everything that you need, every nice map is representable in locally spatial diamonds. So this is something, it's kind of a basic property and homologically smooth. Okay. So if I specialize a little bit further, so I could choose if n is 2, and I have E1 is O and E2 is O of 1, then MB tilde has some much more kind of so what is it? It's like MB tilde is essentially a formal scheme. So it's like I take the formal spectrum of, so K, this was my algebraic closure of FP bar in one variable, and I take the diamond associated to this. right, but I think this is also, you're not so sure? Okay, you don't think it's that. Okay, then let me erase this.
This is the one where if your base change to a field, you get like affine space modulo PP.
But somehow, okay.
And we told this circ is like a punctured formal disk. Or something.
It's a punctured formal disk, okay, but
No, this circ
the circ thing, yeah, okay.
That's important. I need to fill in the circ.
But filling in the circ does not give you this thing itself. Okay, so sorry about this. So let me go back to my safe example. Okay, so as a consequence, let me just state a proposition that kind of generalizes this example. So the map QB in general is representable in locally spatial diamonds. And cohomologically smooth. Okay, and I can even tell you what the dimension is. Cohomologically smooth or relative dimension. Well, kind of this number that you see all the time, so the pairing of 2 rho by nu b. So nu b is the Newton co-character for b, and 2 rho is the sum of the positive roots. So this is also kind of the dimension of a wrapper zinc space. Dimension of a Iguza variety, I guess, yeah. And in fact, sort of QB tilde is an iterated fibration in negative BC spaces. Negative BC spaces. Okay, so in the example we had, it's just literally a negative BC space, but in general, if you have a sort of more complicated, then you get multiple negative BC spaces. Okay, so this QB is a very nice map. The map pi b is more difficult to understand. Okay, so the map pi b is more difficult. Okay, so in our example from before, so this G is GLN, and EB is E1 plus E2. We have, well, basically like, so given S, so if I give you a map from S to Bun G, that means I give you a perfectoid space and an E over it. I can ask, like, what are the fibers, okay? So corresponding to E, so I get, well, there's a kind of Grassmannian of E over this curve XS. Okay, so it's just the usual, I mean, XS you can think of it as the algebraic curve, and then over this lives some Grassmannian of like quotients of vector bundle quotients of E. And so if I look at the fiber of pi b over E, it is given by certain sections of this Grassmannian. And sort of the fiber of pi b over E sort of consists of certain sections of this Grassmannian. Right, namely I need Well, first of all, I need to like fix the right ranks for the sub and for the quotient. Okay, I can do that. And then I need to say the quotient is semi-stable of this, of the right slope, and the sub is semi-stable of the other right slope. Okay, and from this perspective, I want to say it's not obvious that pi b is a nice map. Or at least, okay, so maybe from this perspective, you can see it's representable in locally spatial diamonds, but to see that it's smooth becomes more difficult.
Why did you say E? Oh, sorry.
Yeah, so I have,
E
E is not EB. So I'm saying, given any bundle, I can sort of ask, like, what are all the possible ways it's an extension of E1 by E2? So one way to see that is, first I look at just all the extensions, sort of all the quotients of E of the right rank, and then I specialize to the locus where the quotient is isomorphic to E2 and the sub is isomorphic to E1. So that's a kind of, so it's like sections of the Grassmannian and then some open subfunctor of that, right? So let me just say, from this perspective, sort of smoothness of pi b seems difficult. Right? Like this Grassmannian is smooth. That's suggestive, right? But it doesn't prove anything. And so this is where something called the Jacobian criterion for smoothness comes in. So let me first state this theorem. So this is, again, in general, the map pi b is representable in locally spatial diamonds. And it's cohomologically smooth. Of dimension 2 rho, nu b, again. Okay, and so there's a nice fact that cohomologically smooth maps are open. Okay, so its image is open. So its image in this topological space, Bun G, which is homeomorphic to this Kotvit set, maybe opposite, is this open.
So Paul, I think it's actually true for GLN. You can show that this map is smooth without too much trouble. You can rewrite it as surjections onto a semi-stable bundle, which is open in the Banach limit space, and then look at the subfunctor inside there. Where one of the bundles is semi-stable, which is also open. But the Jacobian criterion really becomes necessary if the group is not GLN.
Okay, so we have an expert comment here saying that smoothness of pi b seems difficult, but it's actually not for GLN. Or it can be done by hand without a Jacobian criterion.
Yeah, I think David has something on his website called smoothness of one end for dinguses or something.
Okay, so yeah. So, okay, but I'll stand by what I wrote.
At some point, Peter had a proof of this smoothness for GLN and for like all classical groups, and for G2 he could prove for all but 1B, but like these were all by hand somehow.
All by
You
hand.
really need this Jacobian thing to do it in general.
Okay, so to me, yeah, it seems difficult, but okay, by hand maybe one can do something. Okay, so so what does this image mean? So for GLN, what are you asking? I say I'm fixing like E1 and E2, and you're asking what bundles can I write as extensions of E1 by E2? Okay. of course, E1 plus E2 is in there, but there has to be more in there because it's open now, right? So it contains this point B, but it must also contain all things that are smaller than B in the usual order on BG. And then the sort of fact is maybe this is open, and then so the image consists of all kind of B prime in BG with B prime less or equal to B. Okay, so this is like, that's sort of this, given that it's open, this is the smallest the image could be. Okay, and again, this theorem, like determining what vector bundles are extensions of E1 by E2, that's in this Arizona Winter School paper. They do this by hand for GLN. Okay, so that's, I think in Fark-Schulze it's one paragraph, and compared to the 60-page papers. Yeah. Okay, so this is enough about the geometry of these things, although we'll come back to more. Yeah, okay, so maybe I'll sort of say the proof is there's this wonderful Jacobian criterion of smoothness. And that's really made for this kind of situation. I have like a smooth quasi-projective scheme over a Fark-Fontaine curve, and I look at the modelized space of certain sections of it, and I want to know when is that smooth, and Fark-Schulze will tell you precisely when. Okay, they say something like, look at the subfunctor of all sections and so that if you pull back the tangent bundle, you get a vector bundle of Fark-Fontaine curve. This has to have strictly positive slopes. Okay, so there's some very precise statement like this. And of course, we know how to compute the tangent bundle over Grassmannian. And in this case, it's indeed going to be of strictly positive slopes. And then for more general flag varieties. Yeah. Okay, so that's I think maybe one of the most technically difficult things. I mean, yeah, at some point there were really talks just about this Jacobian criterion, so it's really a magical thing. So let's see, Fark-Schulze. Okay, so I have about 20 minutes left, so I want to talk about compact generation. Compact generation of D et al. Bun G. Okay, so let me just say quickly, why do you care about compactly generated, and what does it mean again? Okay, so it means, well, generated by compact objects. And who cares? Well, we saw yesterday that so compactly generated implies dualizable in PR. Okay? So this is certainly used at a number of points in this paper of Hansen and Mann. So this is one of the reasons you might care about this. So it sort of links in a small way to the talks of Arnaud. Okay, and so what is a compact object? So this is objects where homing out of the object, so homing commutes with colimits, filtered colimits. Okay, and a fact that I'm going to use that I will not prove is fact. So if I look at this derived category of smooth representations of GQP on lambda modules, this is compactly generated by these objects, compact induction from K to GBQP of the trivial representation of K for K in GBQP, pro P, compact open. Okay, so this pro P is just, you certainly want it to be pro to the order of, lambda. Like, yeah, that's the main thing. Okay, so I have these nice compact operators for these individual sheaves on these individual strata, and I want to sort of, I want to get compact generators for Bun G. And maybe I also want to characterize compact objects. Okay, so first let me use these charts to construct compact generators. Okay, okay, maybe I'll sort of say one thing, like, what is this object? So what is this? This is H lower shriek of lambda for H, the map from point mod K to point mod GBQP. Okay, so the paper of Heyer and Mann explains in a lot of gory detail how you check that the shriek push forward along this kind of map is really compact induction. And I guess the star push forward is the usual induction. Okay, so okay, so I'm going to look at the following map. So fix B and K and JBQP compact open. And I'm going to consider, so I have my MB tilde. So MB tilde maps to MB, and this is a GBQP torsor, so I can quotient out by K. Okay, and then this map is going to be a tau. And then MB maps to Bun G via pi B. And this composition I'm going to call FK. And then I define A upper B lower K to be Fk lower shriek, Fk upper shriek of lambda. Okay, so this composition is cohomologically smooth, so I can form this upper shriek, pull back. Okay, that's just going to be essentially just going to be lambda again up to some line bundle, and then I take the relative homology of this map. Okay, so I know that this map pi B has a certain support, which is like this open sub where B prime is less than B, so this is something supported on that finite subset of Bun G, and the claim is now that these form compact generators. So theorem the collection ABK, as you run over all B and all K, is a collection of compact generators. Compact generators of Bun G. And I'm actually going to sort of sketch the proof. Yes, D of Bun G, dA tau. Okay, so one so let me do a kind of sanity check. So you could ask what is I upper B pullback of A upper BK. Okay, so this is an element of d étal of Bun GB, which we identify with the derived category of smooth representations of GBQP. Okay? And then, so my claim is that this is, again, this compact induction. So for example, when B is basic, so that this stratum itself is already open, I'm not doing something new. So this is just the usual compact generators. Okay, and I should probably add the word pro P here. Pro P. Yes? Oh, it's just that when I was reading these proofs, I looked in Vark-Scholz and yeah, I don't precisely know how this works with devel.
I mean, it really works with demode
Okay.
even. It's all the same.
Right, okay, so all these things I claimed about things being cohomologically smooth, that's true motivically, I guess, because, so Banach-Combin spaces are smooth motivically, or like negative Banach-Combin spaces, for example, and then also this Jacobian criterion, I guess, is also motivically true. So you can check whether the proofs work motivically, if you like. Okay, so how do we do this? So I'm going to use proper base change proof. So I have this MB tilde mod K, and I have my FK to Bun G, and I'm going to pull back along Bun GB, my I upper B, and because I'm doing a shriek push forward, this commutes with pullback. So I can kind of try to compute the fiber product here. And it turns out what I'm going to get is precisely, so let me add a bit to my diagram. So just to make things a little bit clearer, so I have MB tilde mod K, I have my pi B here. And if you compute what this fiber product is, this is just going to be point mod GBQP. Again, this thing I said earlier about the section composed with pi B being the obvious map, that's what I'm using here. And then if I take this further pullback, yes. So this must be this arrow I, this section. And this is also I. Okay, so, well, now it's certainly starting to look like I'm going to get the right thing. Okay, so hence, so this is G, this is FK. So by sort of proper base change, I get that, so IB star of ABK is going to be G lower shriek, G upper shriek, lambda. And then some of the G upper shriek is not going to do anything, so I'm really just going to get the G lower shriek, and that's really just happening here. So I'm doing the shriek push word along this map, which gets me this compact induction, which with some work identifies with compact induction. Okay, so here I'm using kind of proper base change. Okay, any questions? So I guess I wanted to show, okay, this, yeah, so there's nothing difficult going on here. I'm just using proper base change in the six-functor formalism, and then the things drop out. Okay, so proving that these things are compact is a bit more difficult. So the proof of theorem that you get compact generation, so the main input is the following proposition. So let me see where I have this. So for, if I take an object in d étal of, let's just say m tilde b mod k, then I can there's two things I can do to it. The first is I can take cohomology, and the second thing is I can restrict to the image of the section and then take cohomology. So so I can take cohomology, and somehow there's some excision triangle that lets me compare this to the cohomology along point mod k of what I called ik star of a. Okay, so I'm restricting, so MB tilde has this point inside of it, and so MB tilde mod k has point mod k inside of it. So I take my bundle, I restrict to point mod k, and I take cohomology there. And of course, I mean, I know how to take cohomology on point mod k, right? I have a representation of k, and taking cohomology is just taking, well, since k is pro p, it's just taking invariance. Okay, so first, this is an isomorphism, but actually, so we know what this is. So this is just, this is just taking invariance. Okay, so this is a deep fact. So I can't really say much about this. It's sort of saying like, it's saying something is a Henselian, right? So it's saying like, I have a sheaf on a space, and I have a point inside of it, and I'm restricting to this point, and that gives me the same cohomology. So it's sort of saying that MB tilde is contractible. It's like a it's homotopy equivalent to the point inside of it. So the slogan for this is MB tilde is Henselian along the point, and the toy model is. So now you'll see why I wanted to have this spiff. The toy model is that spiff of K polynomial ring T diamond is Henselian along the point. So it's kind of, I mean, this classical fact that on a power series ring, like étal sheaves are just the same as étal sheaves on the point. So that's why I would have liked this toy model, but it's just a toy model, I guess, not the real thing. Okay, so now I'm going to use this. Okay, so again, so now I'm going to prove my theorem. So take bk and take some b and d étal Bun G. Okay, so to understand whether these ABKs are generators and whether they're compact, both of these can be stated in terms of Homs out of them into B. Okay, so I want to compute R Hom from ABK into B. So I want to know that B is, if these are all 0 for all B and all K, then B should be 0. That's what it says to be a generator. And then I want this to commute with filtered colimits in B. That's what it says that these ABKs are compactly generated. So it's nice that we can compute this. Okay, and then we just, well, we do some formal manipulations that I'll give you now. So first I use a junction, right? Because ABK is some kind of push-pull, so I can take one of them to the other side. So it's just the R home from FK upper shriek lambda to RFK upper shriek of B. Yeah, sorry, Vark-Schulze write RFK lower shriek, upper shriek, but I think I shouldn't. Okay, and then I can use smoothness. So this FK upper shriek of B, well, that's just FK upper star of B, tensor FK upper shriek of lambda, and then I can get rid of the FK upper shriek lambda. So this is, so the smoothness of FK tells me this is the same as R home from lambda to FK upper star of B. Okay. Now, what is R home out of the constant sheaf? That's just cohomology. So this is cohomology on, okay, so in these two identifications, I've changed the category that I'm working in, but you can see now we must be working in MB tilde mod K, because that's where FK upper star B lives, of FK upper star B. And okay, then I use this, so here this is formal, and now I use this Henselian property here to identify this with R gamma of point mod K, and then this IK upper star, FK upper star B, okay? And then again, we can try to figure out what that is. So if I go to my, maybe I don't want to go to my diagram. But this again comes down to this computation we did before, that like restricting along this is just restricting to the neutral stratum, the stratum for B. So this will become, so let me just by abusive notation write this as IB upper star B. And that's just IB upper star B K fixed points. Okay, so this is my computation. So I want to know two things. I want to know that, okay, so if IB upper star BK is 0 for all B and all K, well then B is going to be 0 by the semi-orthogonal decomposition. So this tells me that these ABKs are generators. Okay, so that's one thing. And then I want to know that this commutes with colimits in B. And so let's see what did I write about this. So IB upper star commutes with colimits because it's a left adjoint. And taking K invariance also commutes with colimits, basically because K is like a nice thing. So one, so a priori, okay, so one way to think about this, which is maybe perverse, but taking K invariance is just the same thing as taking T lower star, where T is the map from point mod K to the point, right? But since K is like a nice p-adic Lie group, and lambda is a pro P, and lambda is prime to P, T is cohomologically proper. So T lower star is T lower shriek, and T lower shriek commutes with colimits. And, okay, so yeah, T lower star is T lower streak.
I think a more classical way of saying that is that for compact open pro-P groups, K invariants are the same as K covariants, and K covariance is a left-hand.
Right, okay, so thank you. K invariance is the same as taking K co-invariance. In other words, group homology and group cohomology are the same, and then group homology visually, has to commute with colimits. Okay, so I guess I'm out of time, and I'll stop here.